Okay. All right. So since Michael is not here, let me do it. So this is our first event on Periscope, and this is live in Bern at Apps with Love. So today I'm not from Apps with Love, I'm actually from Strong.codes. What I'm doing is just introducing Pascal, who's going to give the talk today. The talk is on security. We explain actually a few best practices to build secure application, and that's it. I think I'll leave you to give this. This kind of lasts for about perhaps 45 minutes, something like this. And then we can have the questions. We can have a few questions. I don't know if people online can also ask us a few questions they have, and we'll try to answer them. Thank you.
Okay, thank you, Laurent. So I'm going to speak a bit about secure software and how to design secure software and how to implement secure software, and see what happens when you have done things right just after, because many things can happen still. Just a very teeny slide about me. I am Pascal Junod, and I have been active in the computer security scene for almost 2 decades, so I consider myself like a veteran. I have two positions. I am a professor of computer security at the University of Applied Sciences in Yverdon, and I am also a co-founder of the strong.codes startup, which is active in the software protection field. And we will speak a bit about software protection at the end of this talk. And my research interests are industrial cryptography, because my background is really cryptography, but I'm very interested in ethical hacking and software security and software protection. That's it. So here is the agenda of my talk. So first of all, I would like to ask a question: what is software security at all? Then we will speak a bit about the good practices of secure software development. I won't go into very deep technical details, because I don't think it's the goal of this talk. Just would like to give you some hints, some good practices, some very generic stuff to have in head when you develop an application, being mobile or not. And then I will introduce a different threat model, which is called man at the end, which is very different and very relevant in our opinion at strong.codes. And then we will speak at the end about software protection and how can you protect yourself from this awful man at the end. So first of all, what is software security, or what is software insecurity? If you have a look at the number of published software vulnerabilities by the CERT, the US CERT, you see that, okay, it's not growing exponentially, but if you look at the very or the end of the 90s, you had a few hundreds of vulnerabilities in many software that were published, and now it has almost 10 times the same number, and there is huge amounts of vulnerabilities on every kind of software, being application, legacy applications, operating systems, embedded software, mobile applications, so SCADA systems, even if you would like to go a bit more industrial. So it means that basically the landscape is quite ugly. It's very difficult to find a piece of software that has been engineered with the best security practices. So there is what security experts call trinity of troubles. So those 3 properties of software results in much of the software vulnerability that you can find. So there is problem of complexity of software, problem of connectivity of software, and the problem of extensibility. So let's. I just would like to go into a bit more details about all of 3. If you just type on the complexity of software, people write millions and millions and millions of lines of code, and this is really growing. Just take an example. It's the number of lines into the Linux kernel. It's very easy to take those numbers because we can count them very easily. it's a bit more difficult to have figures about closed source software, but most of the software follows this trend. You see that it's growing ever and ever and ever. And if you just admit that there is, I don't know, a few bugs per 1,000 lines of codes, then the number of bugs and software vulnerabilities will just explode as your code base explodes. And this is really the case for most of the software that we know about. Now, the second problem, the second trouble is connectivity. Now we have networking absolutely everywhere. We speak about the Internet of Things. Everybody is connected through his smartphone, so Internet is really driving everything in our world. And this fact push people, for instance, to publish online applications that were not designed to go online. For instance, very complex banking applications or this kind of stuff. And when you have legacy applications that were not supposed to be connected, and that you add a layer of connectivity, that you publish it service-oriented architecture or an API, then you open a lot. You open the Pandora box, and this generates a lot of troubles. So connectivity really is a problem. Everything is visible from everywhere in the world, so a lot of things are visible from everywhere in the world, so this is one of the troubles. And the third issue with software is its extensibility. So now most softwares enjoys plugins, extensions. For instance, if you look at the OS level, you can load drivers in a dynamic way. You have scripting capabilities, components, applets, controls that you can plug into your software in a dynamic way. You work, a lot of people work on a very extensible platform like G2E, .NET, or any other frameworks that we are used to work with. And this extensibility opens a lot of functionalities for the developers, but it opens also a lot of vulnerabilities if we don't think about those impacts of extensibility. Okay, so now I have painted a landscape that is not very friendly with respect to security, and actually it's quite a true landscape, unfortunately. So now I just would like to discuss a bit about what are the good practices when you would like to develop an application to gain a good security. So in the abstract of this talk, I spoke about security is not just about doing a pen test 2 weeks before releasing the software or the application. Why? Because if you have not thought about security from the beginning of your design process, then you will just give an open door to your pen tester, and will say, but okay, come on, there is no security at all. So it's a bit too late to have security in this talk. So I will consider first this usual threat model. I love these pictures. I have stolen them from a book about software protection that were written by Colbert and Nagra. And I really recommend this book to speak or to have a grasp of software security and software protection from another perspective as usual. So this is the usual threat model we are all used to think about when we speak about network security, operating system security, software security. Basically, we have Alice, which has her computer here, and she has to protect herself against a lot of threats. That can be a hacker bomb, that can be a Trojan horse, that can be a worm, that can be a virus, that can be many different things. Maybe it's much more difficult to protect against a skilled hacker that will try to steal data from Alice's world. And this is really how you think when you, for for instance, you protect the network of a company, basically you assume that this world here, you can trust it, and everything which is outside the company is untrustful, and you have to protect against those threats coming from outside. And so this will be the third model I will discuss now. So I will just give you a few key points of what two guys of Microsoft have invented, which is what they call the security development life cycle. So historically, it's quite interesting because they began to work in 2000, at the beginning of the 2000 years, and actually at that years, Microsoft had really serious security problems with its operating system. And there was an event that we call a Microsoft Security Push that was initiated by Bill Gates himself, saying, okay guys, now we really need security and to embed security in our development process, because otherwise we will have real trouble, even business troubles, if our software is not secure. And there was a huge security push into Microsoft at that year. And this security development lifecycle now is still developed by and applied by Microsoft. There are also other proposals, but this one is quite classical. And if you are interested in, there is a very interesting paper here available at this stage. So, first of all, just to begin to think about security at the very beginning of your development process. Just a key point, the security development lifecycle was meant to be applied on a waterfall model, but if you extract the key points, you can also think about applying it on an agile development process, or Scrum methods, or anything like that. And that's really the point that I would like, it's to extract the key points here. So the idea is really to think about security from the ground up at the very beginning, and you have to begin to integrate security related thinking into at the very beginning of the development process. It's like it's quite important, because otherwise you will have to correct, or you will have to cope with vulnerabilities that are very costly to protect. And if you think about it from the beginning, it will be much less costly to deal with security. Another very important point is to nominate a person that is responsible for security. It is not necessarily somebody who is an expert in security, but this is a guy who will define security with respect to other developers or to the management, because otherwise security will just be pushed up, because at the very beginning people think that security is an additional cost. But basically, the money or the time that you invest into this kind of activities should reward you later with no security breach or no security, no loss of reputation, no real troubles after no leak of data. And it is quite important to have a person which is responsible to cope with security matters into the development process. Another key point is to identify the key security objectives of your software. I will come back to it later. What are the goals that we would like to achieve? And then, because if we have no goals, we have nothing to do. And to describe the security goals and the challenges and the plans. So if you begin to think about security, it's maybe not such a big job at the beginning, but it will just drive everything fine from the beginnings. So what could be security objectives when you develop an application? It could be to mitigate financial risks. For instance, there are 100 million businesses that have gone to void, to zero just after a hack. Ashley Madison, maybe this reminds you this year. So they had their whole database, customer database dumped, and basically they were just before entering how to say this,
IPO.
to go into the market, the financial market, and they were 100 or 200 million worth, and just because of a single security leak, the value of the company just gets completely destroyed. It could be reputation risks. For instance, if you are a software foundry, you develop applications and then you sell them to a customer, and this customer gets hacked. Maybe it could bring a bad reputation to you, saying, okay, this software foundry is maybe not very savvy with security. Maybe it could be a loss of reputation for you, and this is something that it is maybe not so easy to compute in terms of financial returns at the very beginning, but you can see it on the long term. You can have privacy and regulatory risks. For instance, if you are a bank, you have to comply with a lot of privacy and regulatory rules. If you don't respect them, or maybe if you deal with credit card numbers, you have to comply with rules with the credit card emitters. And if you don't comply to this, maybe your business will suffer a lot from a security breach. It could be in terms of availability. If you sign SLA with your customers and you get breached, and you have to rework and to be offline for 1 week before everything is repaired. Maybe it's 3 weeks. Just have here an example. The Sony PlayStation network hack about 2 years or 3 years ago. They were more than 3 weeks or 4 weeks offline, and the whole gamers community was really not happy with that. Okay, they don't have signed SLA with the gamers, but still, this is really a problem. And you can have legal risks because laws. For instance, if you deal with sensitive data like medical data, like personal data in many countries, then you can just face very legal risks, and you have to cope with them. So your security objectives would be to address all of these risks and to do something to mitigate and to decrease the likelihood of a breach. Then, when you have your security objectives in head, then you can go to the design, and basically during the design phase, security, it's quite important now to define the security architecture of your application, to define what we call the software attack surface, meaning all the input points into your applications, because those input points are the entry point that we have to defend and to protect. And a very important thing to do is to do a proper threat modeling operation. Meaning, if you don't do threat modeling, maybe you will invest a lot of time protecting and a lot of money protecting a point that at first sight might look important, but that is maybe not so important because you have forgotten another vulnerability that has much higher financial impacts, and it may be even less costly to mitigate against. So the threat modeling will just help you to prioritize the efforts that you will invest into securing an application. And you will have to identify the assets. What are the assets of your application? What are the sensitive data? And the risk and their likelihood. Maybe there is a risk with a high impact, but a very teeny likelihood. So at the end, you will have a kind of scale of the things you have to deal with, and the thing that you can maybe just admit, or maybe the risk that you can outsource to the insurance or to a third-party company. And during the security design, you will have to define the countermeasures that you will use to protect your software. Now, what are threats? So just a few definitions, because a lot of people mix those three concepts. So a threat is a person, or an object, or an organization that is potentially dangerous to you, or not. A vulnerability is a weakness. It's a security hole. It's something that will be exploited or attacked by a hacker, for instance, or by a virus. And an attack and exploit is just a technique or piece of code, a little technique, a little hack used to exploit a vulnerability. And the threats can have very different nature. It could be non-target specifics, like the latest one that tries to steal CPU time to send spam, that targets everything it can target, so maybe you will suffer from such a non-specifics. It could be employees. Internal threats are very important, and unfortunately most of companies forget about it. But this is something that a disgruntled employee can do a lot of harm. Some banks have done the bad experience in Switzerland 5 or 6 years ago. It could be cyber criminals. Now you have to know that there are very active teams in a lot of countries that just do cybercrime as a business. Okay? There is a huge market for vulnerabilities, exploits, steal data, hackers for hire, and so on. So cyber criminals can really be a threat to take into account. It could be, and often they are linked to organized crime, so those are not very familiar. It could be corporation. If your competitor is really aggressive, it could hack your application, or it could hack even maybe your internal network to steal your sensitive data. And now we know that when we speak about economical intelligence and this kind of stuff, nations also are very active on this domain, and sometimes they are just not picking information to identify terrorists, but by the way, they also pick intelligence information. So that could be, maybe or not, in your case, a threat to take into account. I don't say that all of these threats apply on all scenarios, not at all, but in your scenario, you have to think about it. And it could be also natural threats, if you speak about disponibility. Maybe if you have your computing center at a location and a replicated computing center just in the same building in another room, maybe you don't have taken into account the fact that you can have flooding on a brand or something like that that will destroy your disponibility. That explains why sometimes there must be a large geographical distance between computing centers. Okay, now vulnerabilities. People have spent quite a lot of time to sort and to identify all kinds of vulnerabilities, and sometimes new ones emerges. There are a lot of different categories of vulnerabilities. I won't go into much details here, but there are books, entire books that describe all these kinds of vulnerabilities. It could be weak crypto, it could be bad code quality, a problem of authentication, a problem of logging and auditing, bad error handling mechanisms, dangerous APIs that shouldn't be used, problem of input or output validation, etc., etc., etc. So for developers, sometimes it's good to have at least a minimal exposure to all these kind of vulnerabilities, to have maybe exploited one of them, just to have a grasp of what is dangerous when writing code, and what can be or what could be dangerous. And then the threat modeling is just a kind of cyclical process. Once you have identified your security objectives, then the goals are really to decompose your application into modules in terms of security, to identify threats to each piece of your software. And when you have identified threats, then you can possibly identify vulnerabilities, correct them, and as soon as your application is developing, and maybe if you are a very agile cycle here, then you have to continue to think about this threat and vulnerabilities identification. There are even standardized methods to do this. I I will just cite a few of them that will help you just list the vulnerabilities and give a priority to them. For instance, you can use strike, dread, try, CVSS, etc., etc. Just pick the one that you like the most, and it will really help you to understand the security of your application and the threat model of your application. And but basically, they all are the same generic goals, meaning it's component identifications, the data flows identification, so who is communicating with, what is communicating with what into the application or with the outside, and define trust boundaries where you can have different security levels if it is required. And this is only everything I spoke about is related to the design phase, and maybe it's the design phase the most important moment or the moment to have the most time invested in to do a proper security goal. And when you have done all of this, then you can go to the implementation. And it is quite a straightforward stuff, and there are a lot of things that can help you to do a good job. Good security means applying adapted coding and testing standards. So if you don't have any coding standards, then you will introduce bugs and software vulnerabilities in the code. It can be the use of specialized libraries. For instance, if I have cryptography in the head, it's really not a good idea to re-implement cryptography yourself because it will be a long work, a complicated work, and it is very, very difficult to have a good crypto code. Even experts write buggy code, and even real worldwide experts do like this. So use really good crypto libraries, for instance, but there are other possibilities like input validation libraries or frameworks and the like. You can be helped by code scanning tools that you can integrate into your IDE. That when you just write your line of code, we say, okay, forget about this string copy function because it's very dangerous and you will screw up with buffer overflows. Or maybe here you printf, it looks like you have a format string vulnerabilities, forget about it. And this is really helpful because it also helps to improve the developers' capabilities online. And there are quite a good tools that you can find in the market. And another important step here during the implementation phase is code reviews. Code review is just giving your code to another developer that reads your code with a security approach in mind and say, okay, but guy, you have done something wrong here. This is not a very, very funny time for a developer because nobody likes to have its code reviewed. But when people are used to it, there is not much problem. It's a bit difficult at the very beginning. And basically, when you are focused on your code, it's sometimes difficult or even impossible to see bugs or to see vulnerabilities just because your mind did not imagine that it could be over here. But when you give it to another person, this other person will just say, oh, and see it immediately. And this happens. I have seen it many, many times, even with very skilled people. And code reviews are really good practice in that field. And then, okay, you have developed your application, you're ready to release. So the idea here, just before releasing, is to do maybe a final security review. Did we forget something? Okay, maybe not. We can do pen tests, but here pen testing is really does really make sense. Why? Because you have thought about security, you have implemented security countermeasures, and then a pen test is here to see whether you have forgotten something or there is a badly implemented security mechanism. So you can go into a white box pen test, meaning you just give your code to a specialized company that will give all the specification of the code, Or you can have a black box approach. It's like hackers. Basically, you give it to a pen test company, you say nothing, and you put the guys, the pen tester, really in the position of a hacker and see what they can do. And the goal of this step here is really to answer the question, is my soft ready to go to production, not from a functionality, but from a security standpoint. And then it's not finished, because you have released your software, and then there is an important phase, which is security servicing. That's the awful updates. So first of all, there is a monitoring phase, because if your application is quite sensitive to security issues, you have to follow a group of hackers or crackers and to know quite quickly that maybe you have a security problem. Because the worst is that one of your customers says 3 weeks or 1 month ago, but hey, you have been hacked about 1 month ago, and if you were not aware about this, this can be a real reputation risk. You have to evaluate the reported vulnerabilities, and there is a lot of different mechanisms that we can put in. We can offer security bounties to security researchers, which is a kind of quite nice way to work with, let's say, ethical hackers playing with your software. You just give a bunch of money to a nice security vulnerability discovery. It works. Many big companies do it, and if you give a few $100s or maybe a few $1,000s, it's much of the time much more worthy to give a bit of money to those guys and to encourage them to disclose their discoveries to you instead of maybe cyber criminals. You have to release patches and sometimes the security advisories if you have a critical software, and sometimes it's on a regular basis. Sometimes, if, for instance, if Microsoft has a remotely exploitable vulnerability in the operating systems, that's very critical, and they have to release a patch in 1 day or even less. And maybe you will have to take response actions like legal actions, or maybe a review of your development and security process, saying what was the problem, maybe we have forgotten to think, maybe we should improve a bit how we work. Just quickly, I would like to expose less than 10 basic security principles that are completely universal and that you must apply when you do secure software. The principle of least privilege: you have to give each component only the minimal rights necessary to carry out its task. It's not very easy most of the time. For instance, if you think about Android permissions, basically it's quickly necessary to give too much rights to your applications. The second principle is the defense in depth. It's good to use several redundant protection mechanisms. For instance, if you have a website, maybe you would like to validate input on the server side. Of course, it's very necessary, but also on the user side. So it means that if unvalidated input arrive at the server, it means that there was already a problem, that somebody played with a JavaScript in your web application or the like. So several redundant protection mechanisms are really useful. User participation. Your software will be used by real people. Real people don't like security at all. And a security procedure or security countermeasure will be efficient only if all its users adhere to its principles. If people don't like your security measures, they will either avoid them or don't use your application or your software. That's very, very important. A choke point is really important when you do your threat modeling, and then when you implement your defenses, maybe with the data validation issues. A security mechanism is effective only if there is absolutely no means to bypass it. So here, think about a firewall and a network, protecting a network. If you have another entry point into your internal network, then the firewall cannot do its job, and he is useless. Deny by default, forbid everything but what is authorized. It's called whitelisting and not blacklisting. Blacklisting never works. Whitelisting is really a good solution for a lot of different tasks. Principle of weakest link, it's quite important in terms of priorities. The adversary will always attack the weakest link of the security chain. So it is not necessary to have a big cryptographic architecture if you don't validate or if you expose your keys, if you don't validate your inputs. And basically, it means this principle says that the security level should be well balanced. Otherwise, it's a waste of resources. Fail securely. You will have exceptions. You will have errors. Maybe when a server is not present. But sometimes you see failure handling that expose a lot of information to a hacker. So always ensure that an exception does not open a security hole. It's not very easy because a developer would like to have a good debugging information, but at the same time, debugging information is very useful for a hacker as well. So here there is a real delicate and good balance to find. No security by obscurity. Okay, I will come back to this stuff a bit later, but what is important is do not rely on the secret of the implementation to keep the system secure. So obscurity won't ensure security. If you have a secure system, then you can furthermore add obscurity on it, and it will slow down the hacker. But obscurity only just doesn't help. And last but not least, simplicity. We are in the town here of this quite famous guy who once said everything should be made as simple as possible, but not simpler. Simplicity is solving the complexity issue, of course. So a simple security solution is much better than a complex one, for sure. Okay, so now let's speak a bit about the infamous man at the end. So now you have obeyed about everything that I said. You have a secure development process, you have good security practices, you have everything you want. And then what happened? Then you get hacked, for sure. Maybe hacked not by a script kiddie, but maybe hacked by a skilled cyber criminal that found really interesting to attack your application because there was a huge financial involved, and he spent a lot of time to work on it. So even if you have no software is perfectly secure, even if you have done a lot of things to improve the security of your software, of your application. But most of the time it happens because of a different mindset of hackers. And did you remember about this? It was a user threat model with Alice here is central, and then you have a kind of shield around her, and she wanted to protect against external vulnerabilities. The man at the end is very different, and it's really the threat model of software, because when you ship software, what happens is that the guys who will attack software will really be protected inside a very protected bubble, and he will have a lot of time and a lot of freedom to do everything he wants about your software here. Okay, it will just not communicate from outside. It has your binary into your hands, into its hands, and it can begin to play with it. And this is really a problem of your software. This is the problem of the man at the end. So you can have very different activities. For instance, could be malicious reverse engineering. So let's say that Doris is a developer and she has developed a nice program, and one of the components of her program is particularly clever, particularly optimized. She's the only one that does this piece of software so well into the world. So what could do Axel is just buy one copy, and either reverse engineering the software and understanding how it works and re-implementing its algorithm and ID, or maybe just do what we call code carving, meaning taking the nice module and put it in its own software and sell it And this reverse engineering or code carrying operation are quite easy, and we have seen them a lot in practice in many different products. It could be digital rights management. Okay, this is DRM, they are not very loved, but still some people try to protect digital assets like this, doing, for instance, taking a media, a video, or a PDF, or I don't know why, and with some business rules, and then everything is cryptographically protected. And what can do Axel is just extract all the protections and either modify the container and give it for free on the internet, or extract the media and resell it. So it could be video, it could be books, it could be music, it could be many things. And this is typically a scenario where the man at the end is very powerful. Now, so the figure is a bit old because it's a supercomputer, but now we can just transpose it into cloud computing world. When you are using a cloud provider, your software that maybe handles sensitive data, it just goes somewhere into the cloud on a server, and you don't know, and most of the time it's on a virtual machine, and you don't know with whom you share your virtual machine. You don't know whether your cloud provider is trustworthy, and maybe it's good to have some protection against your cloud provider. For instance, if you have confidential data or you have implemented very clever algorithms. So, and here we have it, so I have painted a bit the attack scenario. So let's speak about protection, and we arrive at the software protection part. So the idea here is really to bring protections with respect to program reverse engineering analysis, understand how the program is working, and what we will do is to confuse the code, meaning transform it, keeping its functionalities, but making it more difficult to understand. Then there is the temporary phase where the adversary will just modify your software, for instance, flipping a bit in the authentication code and saying, okay, you are always authenticated. Here, what you can do is to protect against tamper-proofing with self-checking mechanism and this kind of stuff. And then you have a third layer of protection that the hacker could distribute unlawful copies of your software. And so here the idea is to watermark your software. Maybe if it's possible, it's not always possible, but if it's possible, to distribute unique piece of software that are functionally equivalent, but that are different, such that you can trace a leak and maybe take legal actions or this kind of stuff. So, defenses, analysis, we talk a lot about obfuscation. So obfuscation is transforming code in order to slow down a reverse engineer. So today, no obfuscation method is 100% bulletproof. What you can do with obfuscation is to buy time to a reverse engineer. And if the reverse engineer needs only 10 minutes to hack your application without protection, but it needs maybe 1, 2, 3 days or 4 days of hard work when it's obfuscated to understand how it works, it's very different, and maybe it will just discourage a lot of hackers to play with your application. Tamper-proofing means putting verification codes and doing very clever stuff to prevent modification, and watermarking, I also already spoken about that. And this is typically how we understand the situation at strong.codes. So we have what we call the opening phase, the analysis phase, the modification phase, and the distribution phase. And there are a lot of tools that are useful to do all these steps. And at strong.codes, so we offer a solution that we call Strong Protect that addresses actually each of the steps. So for instance, for the opening step, we try to detect jailbreaks, for instance, or virtualization for certain software, or that the application is being debugged, and try to detect this kind of behavior of the application, and then to take countermeasures. Then you have the analysis phase, where you would like to protect against reverse engineering. So we have a lot of code transformation that just transform a nicely implemented code into a huge spaghetti, awful piece of binary machine code. That is functionally equivalent. That is maybe a bit larger, maybe a bit slower, but that is much, much more to reverse engineer and to understand. Against modification, we have quite innovative code temper proofing mechanisms that works on Intel 32 and 64-bit and ARM 32 and 64 bits. That when it detects a modification, then breaks the control flow of your application. So the control flow routing is really integrated with the code temper proofing. And then we have the possibility to, because you know that compilation process is, for virtually all compilers, is a deterministic process. We have the possibility to diversify the compilation and to diversify the machine code. Always it's completely functionally equivalent, but you have the possibility to build a unique binary for each of your customers if you are able to distribute such things. So what is actually Strong Protect? Strong Protect is a compiler generating native code. So it's supporting a lot of programming languages. It is based, mathematically, it's an extension of the LLVM compilation framework, which is the open source compiler that is pushed and supported by Apple. And we even, so as it was at the very beginning, it was a research project. We have an evaluation version which is available as open source software at this link. It's called OLLVM, and already a lot of the software mobile application developers know about it. Just to say that it is a very simple version, which is now very much weaker than our commercial product. We support virtually all the languages that programming languages that are supported by LLVM. But to be honest, so we have really a good experience with C, C++, Swift, and Objective-C. We have not played a lot with Fortran or Ada because there is not such a development with that. And what is interesting is that we support a lot of backends as well, meaning a lot of different architectures. So not only Intel or ARM, but also more exotic ones like MIPS and so on. And we support quite a lot of operating systems because some of the constraints that we embed are OS operating system dependent when we speak about, for instance, anti-double matrix. So mainly we have now a lot of good experience with the Apple world, Android world, and Linux, Mac OS 6, and Windows. So how to use Strong Protect? Basically, it's just a new compiler that you integrate as usual into your development, your IDE, and so we have installed it for Eclipse, Xcode, Visual Studio without any problem. It works in your environment, so there is no need to share code with us. We don't see your code. Wouldn't. If you ask us nicely, we will look at your code, but it's really not the goal at the first time. And it's usable out of the box. You don't need a modification of your process. It's compatible with multiple environments. And so you have two ways to operate it, either in a completely automatic way. So we have a profiling-based protection mechanism, meaning that we do a performance profile of the application, and then we re-inject this information just to identify hotspots that should not be too heavily protected because of performance issues. Or you can also, but it is not a must, you can also annotate a precise function with function annotation on the source code, saying, okay, this function is really sensitive, I would like to protect it specially, or this one is crucial in terms of performance, just avoid it. I don't care about security. So there is no required modification of the source code, but you can if you would like. And just to have a bit of comparison between the two open source version and the commercial version, basically we have in the open source version we have just code substitution, insertion of bogus control flow and code flattening, which is static. In the commercial version we have a dynamic code flattening, a lot more code substitution, bogus control flow. We have temporal proofing, function merging, constant encryption, insertion of anti-debugging tricks, basic block splitting, integer substitution, and the profile of what helps you to not to destroy the performances of your application. And just to give you an idea, so we have worked quite a lot on a chat secure app, which is open source and which is both available both on iOS and Android. And basically, in terms of performances, by playing with the apps, we don't see any difference. But what is maybe important is that protection will increase the binary code size, and basically with a lot of protection, you will maybe have a DLL or a dynamic library which is twice as large as before, but not 10 times or 100 times as large, because it won't be usable. And how to use it? It's very easy. So with Xcode, you just have to select your strong project compiler instead of the default compiler, and to put the obfuscation, the protection flags, and that's it. Strong codes is okay. We have worked on strong codes now for almost on the technology for almost 5 years, but we have decided to found strong codes startup only at the beginning of this year, and we are 4 people now. So 2, let's say, security engineers and developers of the compiler, Joan Berry and Julien Rinaldini. Laurent, who joined us in June, who is now responsible for business development and for sales, and myself, which does a lot of thinking about designing new protection and the like. And I arrived at the end of my talk. It was a bit longer than expected. I have been too verbose. We have a website, obviously. We have a Twitter account. You can contact us by email. That's it. So I don't know whether you have questions or you would like that I come back to some stuff.
Yeah, I have a question. We do a lot of backend code in .NET. How do you protect it?
Do you want to repeat the question, perhaps, because you're closer to?
Okay, the question is how do you handle .NET or Java? No, we don't handle interpreted code for the moment. Why? Because so it's a completely different technology, and we think at strongcode that reverse engineering, so interpreted code is quite away from native code, from the operating systems. So it's much more difficult, for instance, to protect it against modification. You can do obfuscation, you can do some code transformation with it, but it's very difficult to have a full protection against it. So usually we recommend, and most importantly in the Android world, into the Windows world, to go to native code for at least certain important parts that are security related, because it's much more easier easier to protect, for sure. But for the moment, we don't support Java nor .NET. But maybe it will come in the future. But that's a lot of work, for sure. It's a different topic.
So Swift is the same thing then?
Swift, we are using a Swift compiler because Apple has a Swift LLVM frontend for Swift, and it is able to generate what we are using, but it's intermittent representation. So what we use is a Swift frontend, and then it generate native code.
Okay.
Any other questions? Okay, so thanks a lot. We have up to 27 people joining online. It'll be fewer now, I guess. Perhaps you were a bit too long.
Maybe, yes.
So thanks a lot for attending. Thanks a lot for the people online as well. And hopefully we'll do that again. Thank you.
Cool. Thanks a lot.